Um, I actually work mainly on food security and food production. I'm in a center called Food Security Environment in addition to the department. And so I work tangentially on energy. I co-advise some students who don't show up when they're supposed to, but other than that, most of my work is on food. So from my interest in food, I've gotten interested in bioenergy. Okay, no, that sounds much better. So most of my work, energy related, is on bioenergy. When we talk about bioenergy, it kind of is an all-encompassing term. It includes things like biofuels, which you probably have heard a lot about, ethanol from sugar or corn. It includes like basic biomass burning, which is still done in many parts of the world for cooking, for example. And it includes just taking biomass and burning it and producing steam to generate electricity. So all of these things come under the umbrella of bioenergy. But mainly what our current bioenergy system is largely liquid fuel based, so it's corn ethanol, sugar ethanol. That's not at all what we anticipate in the future, but that is certainly what we see now. So I think in a couple of slides, just to try to explain why this is an interesting topic, at least why we think it's interesting. This shows you here each point here is a different country in the world, showing you their level of income and their per capita use of cereals, which is the main source of calories in the world. And these are not like cereals in your box, but like corn and wheat and rice. I just want to make that clear. Then you have on the lighter dots, this is energy consumption. So this is sort of the hallmark of getting wealthier as you get lazy and you get fat. And that's sort of at this end. But even down here, and importantly down here, you have more access to electricity, which is very important for development, for improving living standards. And you have more access to food security, which gives you food security. As you get wealthier and wealthier, you tend to transition more to meat-based diets, which take more and more cereals. As you get wealthier, you tend to transition more to transportation that is more energy intensive. And you can argue that there's scatter along this, so we should all be striving to be, for example, down here as opposed to up here, which is probably where the US is. But this is sort of a universal trend. I mean, it's amazing how universal this is. All the different cultures in the world, all the different histories. People are pretty similar around the world. They want energy, they want food. If it was just one of these things, it wouldn't be that difficult. I think it's the combination of the two as we think about the next few decades that really is the challenge. Of course, they're not totally independent. We do use a lot of energy to create food, to grow food, to distribute food, to cook food. But in general, these are two somewhat independent trends going on in the world as incomes, especially in the middle income and lower income countries, improve. So this is sort of part one, I would say, of the challenge, is how do you meet growing needs for both energy and food? And part two is how do you do this while keeping climate change at what we could argue about is a reasonable level? And this is just a summary figure from some studies done by the Energy Modeling Forum. So I don't know if John Wyatt has spoken yet here, but he runs, he coordinates a lot of comparisons of different energy modeling groups around the world. So these are groups that try to project the future of energy demand and supply. He actually teaches a course, I think this year it'll be offered, on energy policy and energy modeling. This is a little bit of a complicated slide, but I'll explain it. So each of these groups try to meet certain mitigation targets. So they're trying to limit climate change to certain levels. And the bottom line is whenever they try to do this, they really rely heavily on biomass. Does anybody know why that is? You've been hearing about different aspects of energy. Why would biomass help you keep climate change to some reasonable level? This is not a trick question, yeah. It's a what? It is a good base load. It does store energy well, so you can use it regularly. But even more fundamental than that. Yeah, I mean, ideally it would be a net zero carbon emission, right? The plants are taking up carbon. You're using them somehow to release that carbon and create energy. And so you're not actually releasing any net emissions. And so in terms of carbon cycling and climate change, it, at least at the best possible case, is a really good situation. Right now, with corn ethanol, you could argue that the amount of gasoline we use to produce it and distribute it and is actually a net wash. But in the future, these models in particular see biomass as a really important thing. That's actually the only part of it. The other part of it, since my student's not here, I can maybe go on a little bit. The other, she's coming soon. Okay. The other part of it, she'll get less time then. The other part of it is that we don't do this yet, but you guys have heard about carbon capture and sequestration, or maybe you'll hear about that later. But you can actually do that with biomass as well. So you're taking up carbon from the air, you're burning it for electricity, and then you're taking the CO2 from that and you're burying it underground. So which is what we call net negative, right? You're getting energy and you're actually putting the carbon underground. So if you're in an energy model, you can imagine you're trying to meet certain mitigation targets at certain costs, and you have 105 different sources of energy. And one of them is sitting there as a net negative emission. You're going to use that as much as you can, right? Because it's allowing you to then produce emissions with other much cheaper energy sources. And so it's an incredibly important component of any of these energy projections. And what this is showing you here is, just look down here, for example, is the amount of energy derived from biomass in all of these different energy models. Now, there are a couple that are pretty low, but all of them are in the order of 100 exajoules. Now, if you're like me and you come from a different field, that means nothing to you. Exajoules is, just a word. Similarly for gigatons, for me that is a little bit easier to think about. But on the order of, say, 1 to 6 or 7 gigatons of carbon a year in biomass that you're using for energy by the end of the century. So to give you some perspective on this, 7 gigatons of carbon would be about the total amount of carbon that's grown in agricultural worldwide every year on croplands. So an enormous amount of biomass. And if you look at, in terms of exajoules, if you had something on the order of 90 exajoules, that would be the total annual energy use of the United States right now. So we're talking about huge amounts of energy coming from biomass in order to meet the previous graph I showed, which is the energy demands, and in order to meet the climate targets. So this is by saying that we see biomass as a potentially huge resource for meeting these dual goals of energy demand and climate protection or climate mitigation. But it raises all these big questions about if you're actually taking this much biomass out of ecosystems and putting them into the energy sector, what does this do to the ecosystems? What does this do to the food systems that we're using that land to produce food? So these are the kind of questions we look at. You can see this is not just thinking hypothetically about the future, but we can already see, well, let me ask you before I show this. How much of our corn in the United States do we use for ethanol right now? Come on, somebody. 12%. 1/3. So those of you who are paying attention enough, you could see that it's actually increased, but only in the last decade or so, to now almost 40% last year, about 1/3. So congratulations. About 1/3 of corn going into ethanol. Some of that ends up being used as feed anyway because you extract all the carbohydrates. You still have these what's called distiller grains that you can feed to cattle. But it's been a sort of unprecedented rapid rise in a demand for some biomass that we traditionally use for feeding livestock. And this is not a simple cause and effect, but this is showing you the international food prices. And hopefully you guys have paid a little bit of attention to the news enough to know that food prices in the last 3 or 4 years have really been going up. And this is not a single factor kind of thing. Food prices are very complicated, but it is, I think, a very big factor, and it's not a coincidence that you see food prices really reversing their historical trends right around 2001, 2002, when you saw the mandates and the subsidies for ethanol kicking in. So we already see implications for the food system, and this is on a scale much lower than what we've seen for these projections out into the future. So how do we actually meet these demands? Now, it should be said that these energy models that are very happily going on using negative carbon-emitting biomass resources are not trying to model the food security or the food production in the world. They're just assuming that that's a different problem. But at Stanford, we like to think about all these problems as one. So the types of questions that we ask in our research, this is maybe a little bit general, but are these types of bioenergy futures, so these very large-scale bioenergy futures, really possible from a biophysical perspective? Can we actually produce that much biomass in addition to all the other needs of biomass that we have? This is more of a, I would say, an ecological or agronomic type question that we've looked into, and there's a lot of remaining questions in that area. And then what does it imply if it is biophysically possible, and even if it's economically attractive, because we know that energy is certainly you know, a major need and demand of people. Thanks. They're going to, certainly in the rich world especially, they're going to want to pay for energy. That could distort the food markets, though. So what does that mean? Again, coming from an interest in food background, what does that mean for food? But not only that, what does that mean for climate then? Because we know that when you drive up food prices, you drive up incentives to clear land. And so there's a lot of questions out there about, is this really a net positive in the end? If you're growing a lot of biomass in the US, but that's just pushing deforestation in the tropics, what kind of net effect does that actually have on climate? So this is, you could imagine a bunch of related questions on water. How much water would it actually take to grow this biomass? Even if it's rain-fed, where is that water being used or extracted from relative to where it would be used in other cases? And I think the third, which is kind of the overall umbrella question, is what's the right way to do this? It's not the case that we can just say this is really bad news or this is really good news. There's going to be trade-offs. There's going to be situations where it probably makes a lot of sense. It does have a lot of advantages. It has a lot of unique capabilities for providing, say, baseload power at some neutral or net negative emissions. But how do you actually do it right without doing it really bad, which you could argue we're doing in the case of corn ethanol right now? We're having probably a net negative impact on climate. We're certainly increasing incomes for a few people, but it's certainly not in any way a major impact on our energy use or our fossil fuel emissions. So we have a bunch of students, as I said, working on this area broadly. Some of them work more on the types of questions at the top, more ecologist type questions. Some of them working more on sort of, I would say, like economics types questions. And then some of them working more on the engineering type aspects of the question, which I think Lena will talk to a little bit in her 5 minutes. So I'll hand it over to her, and then we can have hopefully 15 minutes for questions.